Have you ever just stopped and wondered how the breathtaking digital worlds we see in movies and video games are even possible? From the lush jungles of Pandora to these epic battlefields on your screen. It all has to start somewhere. Well, today, we're going to go on a little journey to uncover the magic behind the pixels. I mean, just look at these. The level of detail is absolutely staggering. These hyper-realistic characters and incredibly immersive worlds have become so common in our entertainment that, we almost take them for granted. They feel real, like places you could actually go visit. But that's the big question, isn't it? How does a computer, a machine that really only gets ones and zeros, start with literally nothing, a blank screen, and somehow build entire universes? That's what we're here to find out. So, we're going to peel back the layers of what really feels like digital sorcery. But what you're going to see is that it's not magic at all. It's actually something way more impressive. Just pure, clever, human ingenuity. Think of this as a journey from the super complex back to the beautifully simple. We're going to work backwards from these incredible visuals to find the fundamental, elegant rules that make every single digital image possible. All right, so let's start right where every digital artist and programmer begins, with a totally blank screen and just a few basic rules. Okay, first things first, we have to understand our canvas. A computer screen is really just a grid of tiny lights called pixels. Now, here's a fun little trip up. Unlike the graphs from your high school math class, where the starting point, 0, 0, is in the bottom left, on a screen, it's in the top left corner. So as you move down the screen, the Y value actually gets bigger. It's a small difference, but it's absolutely crucial. So on this grid, what can we actually draw? You might be surprised to hear that every complex image you've ever seen, no matter how detailed, is built from just 3 basic or primitive shapes: a single point, a simple line, and a circle. That's it. Seriously. Every epic landscape, every detailed character, it all starts right here. Now, drawing a single point is pretty easy. You just tell the computer which pixel to turn on. But drawing a straight line, that's where things get interesting, because a computer needs a specific set of instructions, kind of like a recipe, for every single thing it does. And this was the first huge problem that the pioneers of computer graphics ran into. When you try to draw a nice, smooth, diagonal line across a grid of square pixels, you get these ugly, jagged edges. We call them jaggies. It's like trying to draw a perfect curve on a sheet of graph paper using only the squares. It just never looks quite right. So how do you solve this? Well, the solution came in the form of algorithms. And don't let that word scare you. They're just those recipes we were talking about. They're just smart, structured sets of rules that help the computer choose the best possible pixels to create the illusion of a smooth line. One of the first recipes was something called the DDA algorithm. It basically figures out the slope of a line and then just takes these tiny little steps from the start point to the end point, coloring in the closest pixel at each step. It's a really straightforward idea, but it used some floating point math that could really slow down older computers. But then came an even smarter recipe, Bresenham's algorithm. Now this is just brilliant. Instead of all that complex math, it breaks the problem down into a series of really simple decisions. At each tiny step, it just asks a basic question to figure out which pixel to light up next. And here's the most clever part. It only calculates 1/8 of a circle and then just mirrors those pixels 8 times to create the whole thing. It's just an incredibly efficient way to get the job done fast. And here's the result of that recipe. Now, is it a perfect curve? No, of course not. It can't be. We're still working with a grid of squares. But by following that simple recipe, the computer has picked the absolute best set of pixels to trick our eyes into seeing a smooth circle. Okay, so we've got our outlines. That's a huge step. But how do we turn those outlines into solid objects? Well, we need to fill them with color. One of the coolest ways to do this is with what's called a scanline algorithm. Just imagine the computer's eye scanning across the screen one horizontal line of pixels at a time, left to right. As soon as it crosses the border into a shape, it starts coloring pixels. When it hits the other side, it stops and just keeps on scanning. It's kind of like coloring in a coloring book, but at lightning speed. So now we have solid shapes. But in any busy scene, a lot of those shapes are going to be off-screen or hidden behind other objects. To avoid wasting a ton of processing power drawing things we can't even see, the computer does something called clipping. It basically figures out exactly what's inside your screen, your field of view, and just completely ignores everything else. It's an essential efficiency hack that really makes modern graphics possible. So we have lines, we have filled shapes, and we have a way to focus only on what's visible. These are the fundamental building blocks. Now let's see what happens when you take these simple ideas and you apply them on a massive, massive scale. In architecture, for example, computer-aided design, or CAD software, uses these exact same principles. Every single wall, every window, every staircase in this virtual model is just a massive collection of lines and polygons, all arranged to create a detailed blueprint before a single brick is ever laid. The medical field uses computer graphics to turn all this complex data from things like CT scans and MRIs into detailed 3D models of human anatomy. This lets doctors and students explore the human body in ways that were just never possible before, helping them plan surgeries and, of course, just learn. And for scientists, graphics can transform these giant spreadsheets of abstract numbers into visual models that you can understand in an instant. It doesn't matter if it's weather patterns, molecular structures, or financial data. This process of visualization makes the invisible visible. And this brings us right up to the cutting edge. Technologies like virtual reality take all of these principles and push them to their absolute limit, building entire interactive worlds for training pilots, surgeons, and engineers in these completely immersive and, more importantly, risk-free environments. And that's the real magic, isn't it? All of this mind-boggling complexity, every single character, every world, every simulation, it is all built from the simplest possible beginnings, points, lines, and just a handful of ingenious recipes being executed by your computer millions or even billions of times every single second. So the next time you get lost in a digital world, just for a second, take a moment and look a little closer. Look at the edge of a character's shoulder or the straight line of a building way off in the distance. Because now you know the secret. Now, will you be able to see the simple, elegant rules, the code behind the curtain?